Hello, my name is Ivan Zhang. Today I'm going to talk about simulation of snakes traversing a wide obstacle using vertical body bending. As we all know, snake moves incredibly well in complex 3D environments. They can generate thrust by deforming its elongated body. Previous snake and snake robot studies found that they can generate propulsion using lateral bending to push against the vertical structures on the horizontal plane. However, we knew relatively little about whether they also generate propulsion from vertical body bending and whether they utilize some terrain height variations. Curiosity Lab recently found that snakes can use vertical bending to propel against the environment to move forward. The snake can generate sufficient thrust from vertical bending. This was confirmed by measuring reaction forces from these horizontal rods, as shown here. The yellow curve shows the fore and after force, and the propulsive impulse is more than double of the braking impulse, which implies the snake generates propulsion in the vertical plane. They also found that the snake can do similarly in a channel with one triangular block. Initially, the snake uses concertina gait to slowly move forward, but concertina is no longer needed once it reaches the block and starts using vertical bending. Although animal experiments can help us learn some incredible locomotion principles from nature, it is difficult to measure the internal and terrain reaction forces. Also, animals may be reluctant to move as desired. On the contrary, simulation can resolve these problems. It's easy to run with thousands of trials with different parameters and can output internal and external forces and torques. At the same time, the drawback are that we must design a controller and the results can be affected by more way of modeling. As a first step to understand how to use vertical bending to generate propulsion, we developed a dynamic simulation of snakes traversing obstacles. First, how do we model the snake and the snake steering interaction? External forces include the normal repulsive force, which subjects to the mass spring damper model, the tangential friction force that follows Coulomb's law of friction, and the gravitational force. The key assumption when modeling rods are that their length is much larger than their radius, hence snake can be modeled as a single coherent rod. We assume that the rod mass is evenly distributed and with a constant radius. The coherent rod is governed by internal forces including extension, compression, shearing, bending, twisting forces due to deformation. And the deformation is assessed by the change of rotation and the position of infinitesimal section. The snake internal torque, which is the torque between the two adjacent infinitesimal sections, are given by the controller. All the forces due to deformation are positive elastic forces, while the internal torque given by the controller is the actuator. We first use a simple feed-forward shape propagation controller in our simulation. The hump of the snake propagates down its body. The desired shape is achieved by prescribing the internal torque. In this study, we only concern the case that snake traverses a triangular wedge via vertical bending. Here is a demo of simulation implementation of pure propagation. By propagating its body shape backward to propel against the obstacle, the motion is intermittent without force feedback control. Here we can output driving torque and the terrain reaction force, which are both hard to measure in real animal experiments. We found that the torque's maximum is in the middle of its body. Torque and the normal force oscillate periodically with the intermittency of speed. Remarkably, the peak normal force linear density on the slope is as large as 10 times of normal force linear density on the flat ground. Before we conduct more simulations, we use a simple model to analyze the force, dividing the snake into 3 sections with in contact with the ground: section 1, section 2, and section 3. We can obtain the normal force of different sections in a steady motion via force balance along x and z direction to make the sum of Fn1 and Fn3 positive. Tangent theta should be greater than mu, which implies that the slope must be greater than mu to make possible the traversal. It is a precondition of our problem. When the sum of Fn1 and Fn3 equals 0, the snake must distribute all its body weight on the slope. It is equivalent to the case that its entire body slips down a slope. So we can make a hypothesis that large theta and the small friction coefficient benefit the traversal. On the other hand, we can intuitively speculate that the large wedge has a large contact area for propulsion that benefits the traversal. Keeping the wedge height and the slope constant, if the terrain is smooth, the snake can accelerate and decelerate until it collides with the obstacle. When mu equals 0.2, the snake can traverse smoothly. The comparison is shown in the right figure. When mu equals 0.24, the snake will lift and slip. Starting from mu equals 0.25, the snake can't get through. So here we can define the critical friction coefficient mu star as the largest friction coefficient for successful traversal. The traversal success rate decreases with the friction coefficient, which confirms our hypothesis that small friction coefficient benefits the traversal, but if the friction is too low, may result in difficulty for the controller to maintain a steady movement, as the smooth case shows. Here we vary the slope angle and keep the wedge height constant. With a larger slope angle, the snake can traverse under a larger friction coefficient. The right figure shows the critical friction coefficient increases with the slope. This confirms our hypothesis that large slope benefits the traversal. We also found that the critical friction coefficient is well below the slope, mostly around half of it across different slopes. The friction coefficients are all set as 0.24 and the slope keeps unchanged during the variation of the wedge size. The pushing area increases with the wedge size. With a small wedge, the snake gets stuck. With a medium wedge, the snake barely able to traverse, exhibiting a lifting and a slipping sequence. With a large wedge, the snake can propagate its body shape smoothly. Through this, we found that with a larger wedge, the snake is more capable of traversing with a higher friction coefficient. This confirms our hypothesis that large wedge benefits the traversal. But what if the wedge size is too large or too small? When we set the wedge height as extremely large, the snake becomes unstable at the beginning and when the left side leaves the ground. When we set the wedge height as extremely low, the snake is stuck as if the wedge doesn't exist at all. We can classify the traversal process into 3 stages, the beginning, middle, and final stages. We set the friction coefficient to be 0.28 and then position the snake to different stages and initiate a motion. For the beginning stage and the final stage, the snake gets stuck, while for the middle stage, the snake can move forward, implying that the snake can generate more propulsion against the wedge to move forward at the middle stage. Hence, if the snake is at the beginning and at the final stage, vertical bending alone is not sufficient for propulsion. Other cases, such as concertina, are needed for help. Here, we position the snake to the critical point between the beginning stage and the middle stage, and then initiate the motion. The snake finally gets stuck at the critical point between the middle stage and the final stage. Vertical bending alone may only apply to the middle stage. We also tune the friction coefficient and summarize the state range. Case of mu equals 0.28 is boxed in the color map. The range of the middle state becomes narrow as the friction coefficient increases. Here, friction coefficient is well below the slope, but the snake still gets stuck. That implies that snake cannot distribute all its body weight on the slope. Why can the snake generate more propulsion against the obstacle at the middle stage? Other than force balance, the snake is also subject to torque balance. We can show this relationship in a theoretical model. We assume that the point of force application is at the middle of each section. Terrain reaction force must be positive. However, in order to satisfy the torque balance, the beginning state and the final state gives negative terrain reaction force, which is shown in this animation. Based on this, the model can roughly speculate the range of the middle state. Hence, only when the hump is in the middle range of its body can the snake progress forward. With pure propagation, the variation of snake speed is large. Hence, we seek for a way to stabilize its motion. The control target is tracking a steady speed. The only source for the snake to gain propulsion is through the slope. Hence, managing the force on the slope can be helpful. To keep the propulsion close to the theoretical value of Fn2 in a steady motion, the snake can move forward at a near constant speed after a short period. Here we can conclude that force feedback helps to control the snake's motion. However, how to design a appropriate controller for a snake to perform vertical bending in more complicated terrain remains to be a problem. Finally, we can conclude that small friction coefficient and a large slope benefits the traversal. A larger obstacle is helpful for generating propulsion stably. Distributing the body weight on the wedge in the middle of the snake's body helps gain more propulsion, and force feedback helps to control the snake's motion. As for the future work, first, we need to discover the stiffness rule in the snake modeling. Second, we may generalize the simulation into a 3D case. Third, we will explore force sensing and feedback control. And I would like to thank my lab mates and Henry Astley for his animal experiments reference. Thank you.